Hi, I am Yadagiri Rao. In today's class, we discuss state functions as exact differential and path functions as inexact differentials, and also we cover what is cyclic process, the Euler's criteria for state functions, path functions, means exact differential and inexact differentials for those state and path functions, and how these two will behave in cyclic process. So what are the conditions for the cyclic process for a state function and path functions? Also, we try to cover enthalpy if possible. Okay, now let's go into the class. What is state function? We already know that it is a property or function that only depends on the present system, present state of the system, but not on how it has reached that state. And what is the path function? It is a function or property that depends on how you have reached to that state. Basically, history. It depends on the history of how you have come to that state. And state function is an exact differential, whereas path function is an inexact differential. What is the meaning of path function and state functions in terms of differentials, exact differential and inexact differential? If a function is state function, if it's a state function, any property, then integration e1 to e to de. Here I have taken internal energy as an example. That is equal to e2 minus e1. Then that is known as a exact differential. For path functions, integration like work and heat, integration q1 to q2 is not equal to q2 minus q1, and integration w1 to w2 dw is not equal to w2 minus w1. So now what is cyclic process? A cyclic path, better we can call cyclic path. So let's say I have a system at this state right now, and I have done a process. Now I reached this state, and another process I reached here, and another process I reached here, and finally I reached this initial state. So after a series of processes, I reached my original state. So this path where series of processes are leading to the initial state is known as a cyclic path. In the cyclic path, the integration of a state function over the cyclic path is 0, whereas for the path functions like work is not equal to 0. So we are going to learn these two. Okay. So what is the cyclic process? It is a process or path of several steps leading to the initial point. So that is known as a cyclic process. Now let's go to Euler's criteria for exactness of a differential. So before we go into thermodynamics, let's have a little bit of partial differentiation in mathematics. So that is Euler's criterion for exactness. Let's take a function z equal to f of x y. The differential of z is dz is equal to dou f by dou x constant y times dx plus dou f by dou y the constant x times dy. So you can also write this as a dou z over dou x constant y times dx plus dou z over dou y at constant x times dy. This is a differential expression. It is going to be exact if dou over dou y of dou f over dou x at constant y is equal to dou over dou x of dou f over dou y constant x. So this is a criterion for exactness of a differential. So it may look a bit outside topic, but this is what we require to decide the exactness of a differential for the thermodynamic functions. Now let's take a problem here. What is the problem here? Prove molar volume of an ideal gas. Molar volume of an ideal gas is a state function. Is a state function and it has an exact differential. So that's the question here. So what is the molar value? Molar value is volume occupied by 1 mole of the gas. So for an ideal gas, let's take the equation of ideal gas, that is PV equal to nRT. So from this I can write V over N, which is molar volume of 1 mole gas, equal to RT over P. Now I represent V over N as V prime, or we can write Vm prime, and we have to prove that Vm dash, not prime, is a state function and dVm is exact differential. So if we prove that dVm is exact differential, that infers molar volume is an exact differential. So let's see that one. Now let's take, we have now expression for molar volume is RT over P. So it clearly indicates that molar volume is a function of two things. What are they? It is a function of basically pressure and temperature. So pressure and temperature. Now let's write its differential form. So dVm is equal to, what is that? dVm prime over dP at constant temperature times dP plus dVm dash over dt at constant pressure times dt. This is the differential of molar volume of an ideal gas. Now we have to prove this is an exact differential. How can we prove now? We have to prove taking the Euler's conditions. What is the Euler's condition? This is the Euler conditions. So this one, differentiation of this with respect to t and differentiation of this with respect to p, if they are equal, we call dVm is an exact differential, and that infers Vm is a state function. So now let's take the dVm over dP at constant value. For this we are going to take differentiation with respect to t. So that going to be d over dt. What is this one? Let's find out what this value is. So dV over dP of Vm. That means P of, what is the Vm? RT over P. So that is going to be, if we know the differentiation, 1 over P here. So 1 over P differentiation is negative 1 over P square. That gives negative RT over P square. So let's plug here. So negative RT over P square. So that gives negative R over P square. Why? Because here differentiation of P with differentiation of temperature with respect to temperature is 1. So that gives negative R over P square. Now let's take another one, the second part, that is differentiation of this one, this factor, dou T at constant pressure with respect to pressure. So what is that going to be? Let's see. We know dVm over dt. We must know this first. So that I can derive from, what is the expression for Vm? Rp over P. So that gives differentiation of temperature with respect to temperature is 1. So that gives R over P. And this R over P, let's plug here. So that gives R over P here. So that makes, now you have a 1 over P and we are doing the differentiation with respect to P. That gives negative R over P square. Now look at this term, and in the previous case, this term. Both have given us two things, negative R over P square. So what does it infer? Infer that dou over dou P of dou Vm over dou T at constant pressure is equal to dou over dou T dou Vm over dou P times at constant. So that means Euler's criteria is met. Therefore, what we can say? dVm is an exact differential. So this clearly states that molar volume of an ideal gas is a state function. Okay, right. So dV is exact differential and volume is a state function. Now one more question. Now let's prove work. Many times we understood that, or we learned that work is a path function. How is work path functions? Can we be able to prove it using the Euler's criterion? Let's see. So proving, now what are we doing here? Now we are trying to prove work is an inexact differential. Therefore we infer from that work is a path function. So what are we doing here? Work is a path function and its differential is inexact differential. Okay, now let's take work. We know work is negative P delta V. For small changes, we can say dW is equal to negative P dV. And we just learned a few minutes back, what is the dV? dV is equal to, so let's take molar volume, but 1 mole of a gas, then that's the V only. That is going to be negative RT square over P square times dP plus R over P times dt. From where this has come, this is dV over dP at constant temperature, and this is dV over dt at constant, this is dV over dP at constant temperature, and this is dV over dt at constant pressure. So now same thing we plug here. So from this I can get dW equal to negative P times negative RT over P square times dP plus R over P times dt. Now let's distribute this P into the bracket. So then what we get? Negative P times negative is positive, and we have a P in the numerator and P square in the denominator. So that gives RT over P, and this is negative times positive, therefore that gives a negative, and R times P is RP, in the denominator is a P. So P and P cancels out and we simply get R. So what are we going to get now? So dW we are going to get as positive RT over P times dp minus r dt. So now let's take other way. Let's try to prove dw is an exact differential. If it is proved wrong, then it is obviously going to be inexact differentials. Okay, let's take Euler's criteria. What is the Euler's criteria? This one, now here is a p term and here is a p term. So what should we do? This one we must differentiate with respect to p, and this one we must differentiate with respect to t. So let's differentiate with respect to t, and this term we differentiate with respect to p. So now what I do here, I do differentiation of rt over p with respect to t, that is this one. So what I am getting here, I am getting r over p. Fine. Now let's take this one, that is differentiation of negative r with respect to p. So that gives 0. Let's assume df is an exact differential. Then what happens? These two must be equal to, they must be equal. So that means dou over dou t rt over p is equal to dou over dou p negative r. Is it true? Let's verify. If this condition is met, then dw is an exact differential. So now let's see here. So this left hand side part, which is equal to r over p, and we know r is a gas constant which has some positive, some number, and pressure also a quantity. So this is never going to be 0, and whereas this one is 0. So a number can never be equal to 0 here, because this is a number that has some magnitude. So these two are not equal. So therefore what we can say, dw is not an exact differential. Therefore what we can say, dw is an inexact differential. So this infers work is a path function. Work is a path function. Okay, now we have proved in today's class volume is a state function using the Euler's criteria, and work as a path function using the Euler's criteria. Let's also prove work as a path function, so using the thermodynamics terms instead of using the mathematical terms. So now let's take expression for work. What is the expression for the work? Expression for the work is W equal to negative P external times delta V. So but let's take for a smaller work, that is TW equal to negative P external times dV. So using the Euler's criteria, we proved that this is an inexact differential. Let's see how it is going to be. This one actually an exact differential, and this one we just proved that an inexact differential, and this one certainly a property that dependent on paths. Remember, this is not the pressure of the system, this is the external pressure. So this external pressure can be varied depending on the path we follow. If we follow reversible process, the external pressure and internal pressure are almost equal. The process happens very slow. If the P external is considerably different from the internal pressure, the process is irreversible process. And work extracted in reversible process is always higher than the work extracted in the irreversible process. So they are different. That indicates that work is a path dependent. So let's also prove in other words how. Let's take a process and where we are bringing a change in the state of a thermodynamic system. Let's say this is a volume axis and this is a pressure axis. Now let's say initially our system is at P1 and V1. This is volume 1 and our system finally at pressure P2 and volume P2. So now I can say this point actually corresponds to P2. Now let's say this point here, I can take here, this point corresponds to P1. So what is saying here, and this one is basically corresponds to V2. So now let's take a condition here. So V1 is higher than V2. You can see this is on the right side, this on the left side. Therefore V1 is bigger than V2. Obviously, with respect to the Boyle's law, P2 must be greater than P1. So they always have a inverse relationship. Okay. So now we have the system at a state of P1 and V1, and we do a process at constant volume of constant pressure of P1. So now we do some work here and the system is reaching the state. What is the state here is? This is P1 and V2. This is the process 1. Now it reaches from here to P1 V2 to P2 V2 at a constant volume of V2. So this is second process. So this process is done at constant P1 and this process done at constant, what is constant here? V2. So this is the process. So how much work done in these two processes? Let's see. So here basically we know work equal to negative P delta V. So P and delta V, the product of pressure times volume is work, basically energy. So here if this is an object, this is x-axis, this y value and this is x value. X times y generally that gives you area. So for example, let's take a rectangle. This is the length and this is the breadth. And what is the area? This is area. So here also the area under the curve PV represents the work. So area falling under the curve is work happening in the process. Now let's see here for the process 1. So let's say this is a path 1. What is the path? Path is a series of processes that take place when a system is moving from one state to final state, initial state to final state. In the middle, some other states will come. All the processes that followed in reaching from initial state to final state is known as path. Now let's take here in the process 1 how much work is done. In the process 2 how much work is done. That gives you the work in path 1. So let's take the path process 1. The process 1 happened at constant pressure P1. So external pressure is also say P1. Why I say external pressure P1? Here I said P1 as a internal pressure, that is system pressure. But how do I say P1 is an external pressure? So let's assume that both processes are happening reversibly. That means external pressure is almost equal to internal pressure. Therefore, what is the work done here? The work done here is in the process 1, W1 is equal to negative P, that is P1. And what is the final value? The final value is V2 and initial value is V1. So therefore that gives you V2 minus V1. So that finally we arrive at P1 times V1 minus V2. This is the work done in the process 1. Now let's take the process 2. Here the process 2 happened actually at constant value. There is no change in the value. So when there is no change in the value, delta V is equal to 0. Therefore work done is 0. So this is also equal to, let's say, integral V1 to V2 minus P dV. And what W2, that is integral V2 to V2 P2 dV, and this is 0. Why? This is happening at a constant value. Therefore, what is the total work done in the path 1? That is work in the process 1 and work in the process 2. Therefore, work in the process 1 is process 1, let's say W1 is equal to Roman numeral, that's equal to work done in the process 1. How much is that? P1 times V1 minus V2 plus work done in the second process, that is 0. Therefore, work done in the path 1 is equal to P1 times V1 minus V2. This is the work done in the path 1. So this one actually is equal to area under the curve here. So this one. This is the work done in the process 1. And there is no work done in the process 2. Therefore, this is the total work, the shaded area that has been harnessed or done on the system in the total path 1. So let's bring the same final system P2 V2 from the initial system P1 V1 in a different path. Will that give the same energy or a different energy? So let's see that one. This time what we do, we take the system which is at initial value of initial state of P1 V1, and we are reaching to the final state P2 V2 in a different path. How? First what we do a process where system reaches a state in the middle, that is P2 V1. So here a process is done at a constant value of V1 and reach to P2 V1 state, and from there reach to the final state at a constant pressure of P2, a constant P2. And the first process, that is process 1, happened at constant value V1, and this is P2, and here it is P1, and this is pressure axis and this is volume axis. Now how much it is falling under the curve, that is the work. Area under the curve is the work. Let's see here the work done in the process 1. There is no change in the value, basically no work done. And the second process happened in such a way that it moved from V1 to V2. There is a value change, that means work is done there. Now let's do some mathematics of how much work done in process 1 and process 2. So process 1. So if we do the process 1 in the path 2, that is negative V1 to V1 only, P delta V. That's equal to negative. So at a constant, the pressure is, so pressure is changing, but there is no change in the value. So therefore we can say that here is equal to 0. So dv is 0. And what is the work done in the process 2? That is integral negative v1 to v2, and here the external pressure is p2 times t. So that gives negative p2 times p2 minus v1. So this is the work done in the process 2. Therefore, what is the total work done in the process path 2? That is 0 plus this one, that is minus p2 times v2 minus v1. So I can write this one as p2 times v1 minus v2. p2 times v1 minus v2. Let's see here. So what are the things here? So which is the greater work? So pressure work in the path 2 or work in the path 1? So work in the path 1 is P1 times V1 minus V2. Whereas work in the second process is P2 times V1 minus V2. Let's say path 1. What is the work? P1 times V1 minus V2. In path 2, what is the work done? W2 is equal to P2 times V1 minus V2. Now, these two terms are same. And we already know in the beginning, P2 is greater than P1. So that indicates this term, W2 term, is bigger than W1 term. That means work happened in the second path is greater than work happened in the first path. Therefore, what is the conclusion here? Work depends on the path followed. So therefore, the work done in the second process, the second path, basically this one. Area under this curve is, this is the work done in this process, which is higher than the work done in the initial process, the path 1, this one. So how much is higher? This much is higher. So let's do a cyclic process. So this is our initial state. This is the path 1 where we reach the final state. Let's do other way around. We reverse the path 2. Instead of going from here initial to final, we come from final to initial. So exactly reverse of the previous process. Therefore, here what is going to happen? Okay, let's take a process which is cyclic process. How we have initial state here, that is P1 V1, final state here P2 V2, and we follow the initial path as it is, that is path 1. This is V1, V2, this is P1, P2. So we follow the path 1 as it is. Next, what do? We reverse the path 2. That is, we go from here to here. So initially we gone from here to here, here to here, here to here, here to here. So area under the curve is this one. Let's see, if it is a state function, the work done, if it is a state function in a cyclic process, it must be equal to 0, total work. If it is not a state function, if it is a path function, it should have some magnitude. Let's do this one. So here the total work done is equal to path 1 as it is, W1, and sum of this process, which is exactly the reverse of the previous path 2 we have discussed. So that means negative W2. So what does it means? P1 times V1 minus V2 times P2 times V1 minus V2. That gives us, If I take V1 minus V2 as a common factor, I get V1 minus V2. This is the work done in this process. So therefore this one, is it equal to 0? No. There is a V1 minus V2. So this is V1 and this is V2. This has some magnitude. And we know V1 is greater than V2. Therefore this is a positive number. Whereas this number, P1 is smaller than P2. Because this is P1 and this is P2. So P1 is smaller than P2. Therefore this is a negative value. So therefore here, overall work is negative. That means what happened? System is doing the work or system is receiving the work from the surroundings. So it is negative. The work sign here is negative. That means here system performing the work on the environment, that is surroundings. So a cyclic process which is a clockwise, that is work done on the surroundings. It's a negative. So how we can achieve? So what is this state here? P2 V1 and this is P1 V2. Let's say here pressure maintained same at a constant pressure. This is at a constant pressure. Then how things will change when volume is decreased from V1 to V2? So generally when pressure is kept constant, volume is decreased only by cooling it. So this is a cooling process. Now here it is, pressure is increased from P1 to P2, but volume kept constant. Volume kept constant. How does it happen? This is going to be, so pressure is increasing from P1 to P2, whereas volume is kept constant. Therefore it is a heating process. Now let's go from here to here. So here pressure kept constant and volume increased. How do you increase the volume at a constant pressure? By heating, by Charles law, where volume increases with increase of temperature. Therefore here heating is required. Now here what is happening? This process, we have a volume same and pressure dropping. So that means when heat is lost, the kinetic energy of the system also lost. Therefore their speed of the molecules lost, they become slow and they become cool. That is means we have to cool it. Cooling only makes the kinetic energy loss and makes the molecules to move slowly, and bonding happens. They come closer and the volume they occupy smaller. So this is the process happen. So this work is done in a four process manner and reaching the same final state. Still there is some work done. Work can never be equal to 0. Work is a positive quantity. It's absolute terms. In real life, work can never be 0. Work can be 0, but work can never be negative. And what are the negative sign and positive sign in thermodynamics means? From the system's point of view, if system is gaining the energy or system is losing the energy. That is the point in assigning the signs to the work here. So here there is some work done because there is a magnitude to the work. So that indicates that in a cyclic process, work is not 0. Unlike state functions, in a cyclic process, the change is 0. So volume, we just proved that it's a state function. Therefore, that change of volume in a cyclic process must be 0. So therefore, how do we write for a cyclic process? We write like this. For a state function, that is 0. For a path functions like work and heat, this is not equal to 0. So they are path dependent. If closed path in summation is equal to 0, that is a state function. And this one is a character of path function. We have proved that work is a path function and its differential is inexact differential. And to prove the Euler's criteria for exactness, we have taken the value as a state function and proved it as a state function, and its differential is exact differential. And other topic we are going to cover is enthalpy. What is enthalpy? Okay, according to the first law of thermodynamics, that is delta E is equal to Q plus W. Let's take it for a little change in the process, then that is going to be dE is equal to dQ plus dW. And we know the expression for the dW. What is that? dW is equal to negative PdV. Just substituting this, dE is equal to dQ minus PdV. So from this I can write dQ is equal to dE plus PdV. Now I can expand this one. dQ is equal to E2 minus E1. That means final internal energy minus initial internal energy, less P times V2 minus V1. So that gives us, so dQ is equal to E2 minus E1 plus PV2 minus PV1. I can rewrite this one as E2 plus PV2, and I take minus common factor from these two, then I will end up with E1 plus PV1. Here we define a new quantity, that is E plus PV as H. So therefore I can write the first one, that is E2 plus PV2 as H2 minus this one as H1. So I am getting dQ is equal to H2 minus H1. So here the heat changes. Remember, in the both cases I maintained a constant pressure, T and P, only value is changing. It's a constant pressure process. The heat changes happening in this process of constant pressure, resulting in a change in a term called H, that is called enthalpy. So where we have done this one is basically, let's use the dH, not the dP, dH. So therefore dQ equal to dH. So therefore heat supplied at constant pressure is equal to overall change in the enthalpy of the system. But what is the enthalpy? Enthalpy is the energy associated with the existence of the substance by virtue of its existence, and energy associated with its pressure and value. PV is also an energy term. Therefore E plus PV is known as a enthalpy. So this is very important term actually. So energy is present in the system by virtue of itself having pressure and value. So those two put together, that is known as a enthalpy. Basically that represents the heat content of the system. We call it as heat content of the system. So this is the class of today. In the next class we are going to cover heat capacities, specific heats, and some applications of thermodynamics into the chemistry, that is thermochemistry. Thank you very much.